All right, thank you. Thank you for coming. I appreciate it. Today we're going to talk about some of the architecture effects that we see when utilizing GPUs on different architectures. I think this is super important because people buy GPUs and have no idea what the impact will be when they plug them in. I'd like to give a little background first about the Center for Genome Research and Biocomputing. We work right now with 26 departments across the entire university and a whole bunch of groups outside of our university. We usually complete about 20,000 jobs a day. We have about 5,000 to 6,000 processors going at all times. We're holding about 5 petabytes of research data. And we have quite a few machines with greater than 1 terabyte of memory to allow us to change the scope of work we can do. We did start buying a lot of the Power 8 Minsky boxes with the GPUs in them, and we started then, after those got migrated to the AC922, started buying those. And that's what we're here to talk about a little bit today, is why we buy them, the purpose behind them, and how we use them. Right now, in the last 5 years, there's been about 500 scientific publications associated to our work, so we try and be as impactful as possible. CGRB has a model where we maintain a lot of the software tools for our group. There are currently over about actually closer to 5,000 accessible programs and tools. We spent some time porting them to the Power side, and I'll talk about that in a little bit. The CGRB donates this time to compile these tools. It really enables the infrastructure and allows people to get working. We also have computational staff that people can hire away based on FTE or hour, and they can help them interact with the infrastructure and interact with technology, helping them get that actual computational work done. We build new tools as well, and that's what we're going to talk about today, is the tools that we've built and how they interact with that architecture. The tools are novel and heading in the direction of currently deep learning and machine learning. We started a collaboration with IBM where, as we started to go to the PowerPC 64LE platform, we noticed that there was a lack of binaries over in that space, and what we really wanted to do was bring the binaries over and bring the compiling methods over, and so I paid an undergraduate to go ahead and do that process for us. He actually worked with IBM as an intern, and he put a ton of build scripts up, over 2,000 programs up on GitHub. And people can just pull down these build scripts, run them, and they actually bring the binaries down, bring them up, and make them work. It's kind of nice. Really lowers the energy for people to interact with that stuff. We also do a lot of work with Lance, who's here. Good, thank you, Lance. In the open source lab, and that collaboration is really important to us because it allows us to interact with many of the companies that we're trying to work with and present some of the work out to the world in that context. The OSU OSL has been up for a long time. How long, Lance? What are we 20 years? 15, okay. And we're providing through the CGRB with Lance access to the GPU machines on the AC922s for free. So people can check out AC922s with us, and they can get onto the AC922s with the P100 or V100s in this case. And we do it for free. We're going to get people on there. We don't care who you are. We're not going to try and take anything from you, and we'll give you bare metal. We'll give you whatever access you need. And that allows people to port their software, interact with the technology, and look at it in a unthreatened way, is what we like to think. Okay? Today we're going to look at and focus on 4 different algorithms we've written inside the Center for Genome Research and Biocomputing. And these are really more of the deep learning AI space. And we're focused in on these because this talk is about how GPUs and architectures work together. Now, we're going to go through each one of these first. Individually, we're going to talk about each one of the algorithms a little bit. Then we're going to actually watch them race each other after we've discussed them on GPUs, and we're going to watch some videos and see what the really effect of different types of processing on different architecture and how those occur. Each one of these does a different type of processing. I think that's what's important. The AVN one is the first one we're going to go through, and we'll have in just one second. We saw these algorithms and we started building them originally on the x86 side, and or some of them. And when we started to bring them over to the IBM side, we noticed a tremendous speed up. And so we started this collaboration with IBM to really start investigating that on the GPUs, Power 8 and Power 9. For example, some of them cut their time in half And that was really important to us because it changed the scope of work that we could do and helped us remove bias by increasing more data. And so we put up some of these blogs, like the Spotted Owl one and the Oceans of Data one, which is about the plankton, which you'll see in just a minute. And we kind of give people the impression that, you know, their different architecture does affect things. So let's start talking about these. The first one here is where we're actually working with the Forest Service to monitor northern spotted owl in the northwest area. And we're actually just putting recorders in the forest, and we are generating copious amounts of sound data, and we just record the forest, and then we ultimately want to process through that. We want to track the spotted owl populations and the migration pathways, and even potentially get to where we can identify individual species or individual owls and watch them move through the forest. So as we started to do this, I did this with one undergraduate, Barath, right here. And, you know, we had a lot of stuff coming at us. We had 150 sites of data. It was 250 tera every month and a half to 2 months. And we needed to create a CNN from scratch that would basically be able to mine all of the owl data out of there. And so we went ahead and did that. We created the CNN, and it's been accepted in a paper this past Sunday. And so that'll be coming out. But we started to race them first. We noticed that we had K80s on the original x86 machines. They were donated by NVIDIA for this project. And when we moved on to the IBM Power Boxes, we had P100s. We noticed this tremendous difference. And we thought, oh, is it the P100? And it really wasn't. It wasn't the P100 because ultimately we bought P100s and raced them. And they didn't integrate, they didn't act the same way on the x86. And so we found that the CAPI bus with the NVLink created a pathway of moving data that was so much greater than what we were seeing on the x86 side that it really intrigued us. And as we kept moving forward, we thought, let's start to leverage this CAPI and these interactions in other ways. And so we started to build more algorithms around this, and one of them we called was Casa. So that's the next one we're going to talk about. And Casa is a tool that we created on CUDA that actually does genome sequence alignment. So this is done pretty heavily out there right now in the world of bioinformatics and biocomputing. And we recognized that a lot of groups were burning CPU time just pounding sequence alignment through. And we thought, well, there might be a better way to do this if we really could push data through the bus, and it looked like this CAPI NVLink could do it. And so we built this thing called Casa. And Casa, yeah, I wish we built CUDA. Yeah, that was funny. We built Casa, and Casa allowed us to really interact with the GPU in an interesting way. Again, I have an undergraduate who helped me do this, Ryan Kitchen. He's now moved on and getting paid a lot more money than me. But as you can see, here's our P100s. These are P100s, and this is, you know, us running Casa versus our standard algorithms. Some people out there might know BWA. It's a very famous algorithm. It's Burroughs-Wheeler. We put the BWA and bowtie algorithms alignment pieces into Casa, so that way you could run those pieces and get similar output, or exactly the same output. And you can see with 16 cores, our throughput on the CPU is pretty low. But as we moved on to the P100, it really increased. And we noticed that you get 2 to 3x increase by running the P100 on the IBM platform. So in this case, it was actually on a Minsky. This is when we were on the Minskys, and we were starting to move on these Minskys, and we realized, wow, we could pound data through the Minskys, and especially on those GPUs. It was stunning. Instead of doing 45 minutes for a small file, we were done in 2 minutes. And that really changed people's opinion of using this technology. We had to verify that our accuracy was good, and so we actually, looked through, and we actually were able to become more accurate than them. Our hit rate is amazing, but you can see our accuracy lies above the bowtie accuracy, which is important because bowtie has become somewhat of the de facto standard out there in the biocomputing world. And that really, really gave us confidence in utilizing this technology. So let's move on to the third one. This is predicting ocean health, where we actually drag video cameras behind an NSF ship, and we take the video and we classify plankton. And so we can identify 167 different types of plankton right now at this point in time. And we built this CNN with, it was one of the, gosh, it's escaping my mind here. One of the competitions out there, I can't remember the competition group that was doing it, but it was one of the Data Science Bowls competitions. And then we've taken the algorithm and changed it to make it more accurate. Ultimately, this one generates about, right now, 100 terabytes of data a week at the ocean. And we have to process through that video data very rapidly because ultimately it will create tremendous amounts of downstream data. Every time there's a plankton, it has to cut it out in terms of image. If I go through plankton-rich water, I could have billions of images to classify. It is an alarming process. So you have a finite amount of input data, but then it turns into a tremendous amount of downstream data. Our objectives are really to change the scope of work that we could do, increase the number of species, increase our accuracy, and reduce training time. And the training time one is the big one. It was taking us about a month to train on the x86 on the PCIe, and we've reduced that down to about 7 days. So that was a huge step for us because now we can fit into the limits on some of the cloud services for time allocation. We can only run for 7 days on Exceed, and we had to fit into a 7-day process, and now we could actually train up on Exceed if we could get these guys to buy real hardware, you know, some AC922s. And so we've been starting to talk with them about that. Again, an undergraduate named Michaela worked on this project, and she'll be working on some of the other projects you'll see coming down. This is the famous image that's out there that we put out. You drag the camera behind the boat, the plankton feeds everything, and so it really is about ocean health. And we actually were able to scale this one up. Going on the AC922 allowed us to rewrite the grant, show people what we could do with it, and we got funding for 4 countries. And now we'll be doing it with Brazil, France, Japan, and the United States. So this is going to be massively scaling up. Let's see. As you know, it's important that we realize that there's 2 steps to this one, along with the avian one. And that was segmentation and classification. And this one actually leans pretty heavily on the segmentation side. And we realized that the AC922 came with 2 parts. There was a lot of processing capability on one side, and there was a lot of GPU capability on the other side. And you could leverage them at the exact same time. And so we are actually using the AC922 like it's a cluster in a box. You can segment on one side while it's classifying on the other, and you've got full go. It is really impressive. The limit actually became the network, and so we had to start putting 40 and 100 gig on the machines to actually keep them hopped up and keep them going. Okay. The 4th algorithm we're going to talk about a little bit is a newer one where we've actually created a process where we can identify different grass seed species and separate them. And this one is utilizing TensorFlow, things like this. We have an engineer and a CS student helping us. Our goal is to get to about 14 seeds per second and make sure that we have 100% pure one type of seed in the bag. If you've ever looked at grass seed, they'll only go up to about 99% pure, and that's because there's no possible way for them to actually separate out the grass seeds effectively unless it's done by hand. And so there are people at Oregon State, because we are the grass seed capital of the world, there are people at Oregon State who literally sit with microscopes separating grass seed, and they get paid all day to do that. And it's an alarming process, but grass seed is super small, and it's super hard to deal with, and it's super hard to see. And so that's one of the goals that we had in this one. So here's the scanner, and you can see these seeds are actually in macro lenses, so they're actually been blown up. But our goal was to be able to say that's a good seed and that's a bad seed. And this came from a lot of training data. So although we're running this on a desktop with a desktop GPU, we actually had to do all the training data on the AC922. And so without training over on the AC922, we were going to take exorbitant amounts of time. And you got to realize I'm paying people to do this. I'm going to pay somebody to sit there and watch the training go? That's not going to be good. And they're waiting for that to finish to see what the next step's going to be or how, what the effect was. So in the end, if we could massively reduce that training, it keeps people focused, keeps them on task, and keeps them going. So this led us to a project that I worked with Tech Data a little bit because I had to get some extra hardware in. And we really wanted to create a demo site around this concept of seeing how the speed up and the change occurred with the same GPU across different architectures. And so we started this with an undergraduate named Mazen. And Michaela has now taken this over as she's migrated off the Plankton algorithm. And so they've created a website that shows these differences between GPUs, and that's what we're really focused in on today. Each machine in these examples will be running side by side. And we can choose the machines that we want, along with choosing the number of GPUs and things like that. It really was focused initially on the PCIe versus the NVLink, because at the time, NVLink was only available on the IBM side. And as we move forward, we realized that the DGX and DGX2s were bringing in a new flavor of NVLink on the PCI or the x86 side. When that was occurring, we really wanted to make sure we had those too, and so we included some new data about the DGX2, and we've raced those as well. Okay. We did talk with Dell and a whole bunch of the computing groups who sell a lot of the x86, Advanced High Performance Computing, HPC, and they did communicate up until the beginning of this month that people are still buying PCIe-based x86 boxes. And it has to do with the price. It just simply is the price. And people are deathly scared of the DGX because of its price. And so we've recognized that the AC922 sits in the middle, is a really good price point to actually be able to embark on moving data on the GPU without having to ensue that cost of the DGX. And so let's go through here and let's look at this demo. So the demo that we're going to start with is really what's focused on that PCIe, and it still is because Dell, who also helped us with this a little bit, really wanted people to understand the difference of putting GPUs on different things. And they wanted people to stop putting desktop GPUs onto servers. That was one of their goals. Because they saw a lot of people putting desktop GPUs onto their servers, breaking EULAs and all kinds of stuff. We were running 1080s to race those in this demo. We dropped that out of the demo because it was just such a bad card. And it took so long to run this stuff compared to these GPUs. I mean, we're talking like, 10x the time sometimes. So we dropped it. It was going to take too long to show in the demo. But really, these are the two pieces of hardware we focused in on. The IBM AC922 has 4 V100s in it, 32 gig. And then we have an Intel Xeon. It actually has 5 V100s in it. It was actually able to hold 5 of them. And so they're very similar. And they were actually very similar in price. Believe it or not, they're within about $5,000 to $6,000 of each other in terms of cost to me. And that's because the GPUs are actually the main cost. They were very expensive when we were putting these up. They were probably $13,000 a piece, maybe. And so we tried to configure the machines exactly the same. In this case, the AC922 is at 2.2 gigahertz. We bought a 2.2 gigahertz down below on the Xeon side. The Xeon required us to back the processor down. And that was because we wanted to hook up so many GPUs, and there was only so much power going into the box that they actually reduced the processor. The DGX does not do that, but the amount of power going to the DGX is alarming. So this is a consequence that we see, and we want people to understand that consequence. So as we go forward, we're going to sit here and we're going to run a video where we are going to run the avian algorithm. Okay. Now I sped the videos up to reduce the time for this presentation. But this avian algorithm is really about moving data on the bus. And so it's going to try and move the data across the bus, and we're going to see the reaction of that. Hopefully. Here we go. So it's a little bit hard to see, but as you go, you can see that the left side's already started, and the right side's trying to get going. And that was a really important piece right there, is that as we get going, the AC922 immediately starts interacting with the bus, immediately starts loading the data, and starts your processing. And so that right there made us realize that there was an interaction problem just talking to the GPU to begin with. But then, when you got on the GPU, sending data through the bus became prohibitive. And so, as we went through on this one, we get a 2x to 3x speed up just by plugging. It's the exact same code, guys. We did no change to the code here. We just dropped the code on the AC922 and watched it go almost 3x faster. And it was like, yay. No programming, no effort. All we had to do was have the right version of TensorFlow. And with Power AI, okay, well, Watson machine learning, whatever we want to call it today, Power AI, it was super easy for us. I want you guys to also appreciate that the values on the plots are very consistent on the NVLink and on the AC922 and go up and down. It's very noisy on the PCIe and the x86. And that's just the way it's always been, and we recognize this. So when they finished, you were at least 2x from the, uh-oh, I think I just lost power. Hold on. Sorry about that. So the speed, is there power up here? Maybe I didn't see it. Ah, here we go. So the speed of moving data across the bus is really what we were focused in on. And that became ever so crucial because we were working with 250 tera worth of data every couple months. Come on, baby. And the Forest Service really wanted to scale this algorithm up pretty heavily. And as we wanted to scale it up, they wanted to put, we were working currently with 1,500 recorders in the forest. They want to scale it up to a lot, much greater than that. And they wanted to ultimately, potentially even go into real time. So we're looking at how we're going to be able to start interacting with the data in a much greater capacity and do it in a way where we, okay, here we go. Maybe. See if we can get this back up. Oh, are you kidding me? It just unplugged itself again. It was up. As soon as I touched the video, it unplugged itself. Technical difficulties. All right, let's try it one more time. And the same thing occurs on the plankton side. So as we segment again on the owl, the segmentation is based upon how many owls made a sound in the forest. Now right now, we started with owls. We are sitting at 11 species of owls and we're moving to more than that. We also are now picking up squirrels and various other species in the forest. So as we scale, every single time we find a new species, we're going to have to capture that piece of information and classify it. It's the same thing as the plankton in so many cases, where everything that we do is not based upon the raw data that comes out of it, it's based upon the segmentation of the raw data. All right, let's see if we can't do this again here. It's opening. Hopefully. All right. Moving on. All right. All right. So there was the avian, and those are the exact same GPUs, and we saw 4 minutes versus 7 minutes. As we go forward, and we did the DGX was actually running NVMEs and not SSDs, and so we configured NVMEs on our AC922 as well. And this one came in as the AC922 does it in 3 minutes and 14 seconds now, so it does drop. And the DGX2 got down to where we were with the SSDs on the AC922. So the NVLink works on the DGX2, but it's not the same. And working across that bus is just not the same in terms of moving data. It's getting closer, but it's not the same. Even when that DGX2 had 8 NVMEs in a RAID 0 and we had 2 NVMEs in a RAID 0, they were still not there. So as we move on, here's the plankton algorithm. This is the one where we mine the plankton out of the ocean. And if we let this one run, this one's a little different. It's transactional. So we go on and off, and if you watch the left-hand side, you can just watch the transactions going, whereas the right-hand side is not. And that cost of getting on and off the GPU at the beginning is really, really hurting us here, okay? The jobs are small, they can fit on the GPU no problem, and when they get out there, they just sit on the GPU. But the process of getting on and off constantly is really taxing the data processing pipeline. And this one we get a much greater return, and it's simply because of that on-off effect. And so the Plankton algorithm really, really loved the AC922, down to where NSF was looking at putting this product onto the ship, because we realized that it went so fast that we would actually be able to process the data before the ship got back to dock in the 5 days that it was traveling. And we thought, wow, that is really impressive. And NSF is right now in the process of thinking about putting this onto the ship. So as we went forward, those were your times, 3 minutes versus 8 minutes. And the segmentation side is even faster. So we got about a 2x on the segmentation side, leading us to between a 5 and 8x speed up, depending upon the areas that we go through and things like that. And that's based upon how many things we segmented on one side and how many things we classify on the other. The more things we have to classify, the better the return every single time. And that's the cost of going on and off. So we try and get companies to realize if you're using GPUs for transactional data, you better be on an AC922, or otherwise you're just throwing your money in the trash, because you could have been doing so many more transactions, generating so much more money on the same piece of hardware, on the same power footprint, doing nothing different, okay? Same code on all these guys. So here's our Casa algorithm. Now, this demo, I really wanted to show what the effect was if the data went directly onto the GPU, did not really interact on the bus at all. So we created a very, very small data set to align on this one because we had better control. And we did this one so that you could see that the GPUs were really matched. And so as we go and we do this demo, both of them load the data. The PCI side is still a little bit noisier, but it shouldn't have any data really going through. There's really down there at 0. And they go through at the same speed. So the GPUs are exactly the same. And they show that they're exactly the same. If you can go out there and you can do a simulation on them, you don't need an AC922. You go back to your x86 box, you're fine. But you have to make sure that your work completely sits on the GPU, never leaves the GPU, and never has to interact with memory, CPU, or any I/O. If that's the case, then sure, you're fine buying a GPU, a PCI bus, or something along those lines and slapping it in. So these were your times. They were exactly the same almost every single time. They're a little bit noisy on the PCIe side, and that's because we had to get on the bus initially, but they're effectively the same statistically, okay? As we went forward, I want to show everybody the times on the DGX. The DGX2, it gets a lot closer to the AC922, but its cost became prohibitive. I mean, you're looking at $400,000 for one of these things, and we buy I could buy 4 AC922s for a lot less than that. And so cost for performance is not there. The other thing that we figured out that is the DGX is so large that if you try and do bare metal on it, you're going to have a lot of people interacting with each other and kind of banging against each other, whereas the AC922 really allowed us to put bare metal to a single group and allow them to interact on that bare metal by themselves and not have to try and leverage the piece of equipment across multiple groups in that case, and created a single context where I could almost containerize the machines. So they were cheaper, more accessible, and more usable to my researchers. They were also faster. The last one is if you look over there at Casa, Casa does a better job of taking advantage of the NVLink. That 1 minute and 14 is the exact same time, basically, that we got on the PCIe bus. So and this was where we actually used 2 GPUs on this. And the NVLink interacts differently on the power side than it does on the DGX. And so you really didn't see any kind of considerable difference because the thing sat heavily on one GPU anyway on the x86, on the DGX, but it did drop on the power side. So we really saw the NVLink actually work properly on the power side, and that was important. So we thought, let's put some real numbers behind the whole machine. let's see what's really going on here, because we saw a real speed up on the CPU side and we saw a massive speed up on the GPU side. And so as we went through and we started putting numbers to stuff, we had EPYC 7601s, we had Xeons, and we had Power 9s. And, you know, we just started racing them, having some fun. We thought, let's take a 3400 megahertz Xeon. It was super fast and people loved it. And they always talked about how much they love this machine. And I raced it against the Power 9, and I raced it against the EPYC 7601, which is another machine. All my people were saying, oh, they love this machine. And I thought, okay, well, let's race them. So when you just did the Fibonacci, you could see that the Power 9 won. And we were like, yeah, that's what we're seeing. We're definitely seeing that. But we definitely saw a different effect, was as you threaded up on the Power 9, it got a lot better. Okay, and so the EPYC was continually beating the Intel as you kept threading up, but the Power destroyed it. Okay, it was amazing to watch the Power go. And my users immediately were like, wow, and started buying Power boxes. And that's one of the things that was selling it, was the fact that with no code change, we got a 2x return. I mean, and it was basically the same price for the machine. So that's phenomenal. When this is a machine without GPUs, or this is the machine with GPUs, we get the same CPUs on either side, and you can choose to buy one with or without. And so my users could buy machines with just CPUs, they don't need GPUs, or they can buy it with both. But then we said, let's go and do the GPUs, or let's go do the memory, the CPU, and the bus. And let's benchmark these. This is awesome. So when you did a benchmark where I tried to identify the total number of events that we could do within the same amount of time, the AC922 did almost 3x faster than the CPU you would get on any other box that we'd buy a bunch of GPUs on. So that machine that you saw earlier, where they were both matched 2.2s, that's this box, and that's what we were racing here. And you get a 3x performance increase on the CPU side. And that's using the exact same number of threads. Now, the Intel box in this case only comes with, I think it was 96 threads, whereas the Power 9 gives us 160 threads. So not only did each thread go 3x faster, but I got almost 2x of them. And that's where you're getting that 4 to 5x increase on the CPU side if you're really going at it. It is impressive to see. As we go down, you can see that the DGX, and this DGX was a 2.7 Platinum. It's brand new, okay? It's still 3x behind on the CPU, okay? It's just funny to watch. When you watch the Power side finish and you're like, wow. And then you watch the DGX still going, you're like, bummer, because you spent so much money on this thing. When we got down to the memory, we recognized that there was, the Intel was winning on the memory. This was because the benchmark we were running was SSE and SSE 2, 3 enabled. And it was able to see and take advantage of some memory libraries on the Intel side that we do not have on the other side. And so the code itself was focused in on those memory libraries. And so that created a slight bias. And we were looking for benchmarks that don't have that. But it's hard because we've collapsed into that x86 world so badly. And everybody who wants to show benchmarks wants to show the best that that thing can possibly do. And so those libraries were interacting. But the AC922 wasn't that far behind, and we're not heavily using memory on these GPU jobs. And so that's an important feature. As we kept going down, the I/O was the important piece to us. How are we moving data across that bus, and how did that bus affect that? And that's what this was about. So we have two boxes here, green and orange. The green represents the SSDs against the PCIe-based Intel box. And you can see that we're basically 3x the I/O on that. And so that's where we were seeing the change, was the 3x of the I/O across the bus was massive to us. I mean, when you're talking about 100 tera a week coming from the ocean, I got to push that data across the GPU, 3x is important. As we went down to the AC922, you can see that the NVMEs on the AC922 are still faster, and that's the CAPI. The CAPI bus is super duper. And ultimately, we're still getting better performance. So the DGX does start to catch back up and put us into some numbers that are closer to what we see on that SSD side again, but they still aren't matching what we can do on the AC922. Now, I would love to be able to expand out the NVMe capabilities on the AC922. That's where the DGX is winning, is we're getting more space. So we have like 20, 30 tera of NVMe versus a smaller amount of space. And so I think that that's your limit on the AC922, in my opinion, and that's the thing that's upsetting me, is that I want to put a crap load of NVMe on there so that way I can use it as scratch space on that local box and go like a bat out of hell. But I'm limited on slots, and I'm limited because I want to put a 100 gig card in there to keep it popped up. I've got to do some other things. And so, you know, we're communicating that, but that seems to me to be the only limit right now on my AC922. We can go to 6 GPUs if I really want to on it, but I have to liquid cool. That's still not a limit to me. It's a bummer, but it's not a limit. So I feel like the lack of the expandability on the NVMe is the only limit I've found on the AC922. Other than that, it goes so fast it almost wants to take flight. Okay? So, you know, when we were using you know, these machines, we recognized that compiling the software was ever so crucial. And compiling the software to work properly on the Power 9 had to be done properly, otherwise you didn't see the acceleration. So we watched a lot of people pulling down Miniconda packages from Anaconda, which had an old version of TensorFlow, running an old version of CUDA, and was compiled on the Power 8 box. And you didn't get the same return of value that you would have gotten if you had sat there and hand-compiled Bazel and hand-compiled TensorFlow and Python and all these things on the box itself, where it was recognizing the accelerator and how it worked. And so as we went forward, we recognized that the Power AI, Watson Machine Learning, is the tool to overcome this problem for us. So it actually was able to be compiled based upon the acceleration, created a very, very low energy for my users to install it. And it works on both the x86 and the Power side, the same. So we can pick out the version of TensorFlow I want on both sides. It's optimized on both sides. I don't have to worry about this, and I get all my speed with no energy and no effort. And this has been brilliant. And so most of those algorithms that were running TensorFlow and those things were running Watson Machine Learning on the back end. So that way we got the acceleration. We did have to hand compile some of the stuff to make sure that it was getting the same speed on the x86 side, because we wanted to make sure we weren't getting any bias over there. But we got the same speed whether I hand compiled on the DGX or the PCIe or I used Watson Machine Learning. So they clearly went through and they spent their time making sure it was optimized and getting everything done. We have a lot of people involved in this stuff. I have a lot of undergrads. Yes, these are undergrads who wrote these code with us. One undergrad did each one of those algorithms with me. We have really impressive undergraduates, and they go out and they get great jobs. But you know, we challenge them. We push them really hard. You know, you want to be my undergraduate, you're going to have to work really super hard. I appreciate you guys listening. That was the gist of it. I hope you guys understand that there really is an architecture dependence depending upon where you put your GPU. It's not the GPU, it is the architecture. Thank you. Questions?
So on your first graph, at least the first one after I walked in, you were showing what I think was GPU stalls based on the memory, or the memory access rates coming in. The graph on the bottom, I think, was your memory access rate.
Let's go back, okay. Is it for the Casa one?
Either Casa or just before that. You had 3 of them.
This one?
Where you did the video.
Let me see here. This video. Oh, you're talking about these?
This, yeah.
Okay, so these are, the dial is the GPU load, okay? The top one is the GPU memory, and the bottom plot is the GPU I/O. Okay. So that's the I/O bus.
So I like the way on the left you've got the 2 graphs that are kind of maxed out steady state. Right?
Yeah.
But the right side, the implications on the top graph is that it's stalling out because your I/O rate to the GPU is stalling out.
That is correct. That is exactly correct. That's why we did this, is that we got people to visually see what was really happening and where you're losing it. It's because of the I/O. It has nothing to do with the GPU. It's only I/O. And every time it has to dip, because every single time it has to go and interact. And that's that transactional problem. That's what that gets expanded so heavily in the transactional state. So, yeah, John.
Okay, so on the, you mentioned experimental for the AC922 versus experimental for the DGX, which experimental for the DGX is so incredibly expensive, it's not even popular.
Yeah.
But when you did, so on the DGX, you typically run Docker, things in the container. Did you run the AC922 versus the DGX in the Docker container? Did you see?
So we ran the DGX in bare metal, first of all, for all those tests. So I had 16 GPUs accessible to me. We just limited the number of GPUs for the job. So that way I was bare metal on both of them. We do know for a fact, Charlie and I both know, that if you put anything into a Docker or into a libvirt, you are going to reduce down its throughput. And so we've shown that.
How much difference did you see by putting it in Docker?
So like if you take that Casa that came in on the AC922, it was perfect. It's 1 minute and 14 seconds every single time. It's so consistent. It'll go up to about 1 minute and 25, minute and 30.
So that's a lot of overhead by Docker.
Yeah, I mean, and then when you do NVLink, you don't get back the NVLink when you do it because it's confusing which GPU it's on the bus and all this kind of stuff, and so there's a delay in there. And so, you know, we can light up multiple GPUs, but the problem becomes worse. And so you get a worse return. And so if you really want to do NVLink across 2 GPUs, you really want to do it on bare metal is what we've seen. Yeah, because then you don't have any of these. I mean, that was NVIDIA Docker, by the way. That was the NVIDIA Docker. Yeah, you don't have any of those downstream problems. Yep, that's very true. Yep.
You mentioned that you did a number of hand compiles and stuff.
Mm-hmm.
Did you notice a difference with doing HandCompile versus what IBM
Watson Machine Learning
did?
So when we hand compiled everything, we were originally doing that, and then Watson Machine Learning came out basically the exact same. So we bailed on hand compiling at that point because it was a pain in the ass. And I mean, it was like, you know, root canal or compile TensorFlow. I'd rather go for the root canal. So in the end, we got basically the exact same time and it was Power AI when we started. And when we moved over to Power AI, our problem was versioning. We were coming from an older version of TensorFlow at the time in Keras. And so we just had to do a little bit of coding to make sure that we met the new TensorFlow, and that's it. But yeah, we were getting the performance. So there was no question.
And then on your open available environment, you give GPUs for people to play with and stuff.
Yep.
Or is it mostly students or?
No, it's mostly companies.
Yeah.
Yep. The students, I put them over. I have an entire teaching environment and the entire deep learning clubs with me, and we give them separate equipment. So they don't interact on that side. We don't want them to interact with the machines that we're trying to present to the world to allow other groups to come in. We're really focused on scientific binaries, groups who are working with us and trying to change the way that they're doing computing. So we helped Julia port their code over onto the Power. They still do it in a continuous environment. And what we do is we start them on my side, and we a lot of times will potentially migrate them to Lance's side. So Lance has the continuous development environment. He runs the full Jenkins. And so we let them make a decision. They get the full gamut of opportunity. They can pick whatever they want. They can pick bare metal, VMs, have root access, whatever they want. They get to choose. And then we back off. And it's a lot of times companies who are trying to do video processing, things like this, and they're investigating this architecture. I'm talking right now with David and Nereid about testing this on that exact same thing. And so we are really focused in on how companies can do it, because companies allow us to get that code, get that hardware, and change the way we're doing science. It really does change the scope and remove bias. The students, we give them access through the back end. So we have our own machines that are owned by Oregon State University that we've paid for, and they get those machines. Yep. The relationship for those other machines is based upon IBM and stuff. Okay. Anyone else? I really appreciate you guys coming. Thank you.